So thanks for this opportunity to address you. So the plan is just to give a very loose sketch of things I've done the last couple of years to do with higher graded geometry and some implications in physics. So the plan is sort of have a very gentle introduction to supersymmetry, what I mean by graded, a little bit of geometry, and then I'll try to explain well, that's not really enough and what I've done since with it. So to recall supersymmetry, well, before that, you've got to remember that in nature, it's an observed fact that we have two kinds or two sort of families of particles, fundamental particles out there, and that's bosons and fermions. So the important thing is that bosons, these particles, they kind of like each other, they like to hang around with each other, and given the right conditions, they'll all sit in the same quantum state. Yeah, so they like to be with each other. Good example of this, it's all well known, are photons. And then the flip side of that is this other kind of family of particles that are the very opposite. They don't like to be together. They like to stay apart. Technically, you can only put one of them in each quantum state at a time. And these are the fermions. Well, an example of this, the electrons. Yeah, so this is two kinds of very different behaving particles in nature, fundamental particles. And what supersymmetry does, it's a non-classic, very interesting symmetry that unites these bosons and fermions together. So I can take a boson and I can send it to a fermion and vice versa. And this allows us to sort of view bosons and fermions as being two sides of the same sort of coin. So we have these two families of particles that behave very, very differently to do with how many you can put into a quantum state, but supersymmetry kind of telling us they're not so different. So it's a very remarkable, unexpected symmetry. Again, there's lots of nice mathematical results coming from this, but we'll just move on for the moment. The important remark here is even though the supersymmetry seems very natural in a sense, it's a wonderful symmetry, it makes a lot of things work really, really nicely, it's not been observed in nature. So we don't know why this is the case, but we have this nice symmetry. And for example, the LHC at CERN and other experiments, at least for fundamental particles, have just not seen any hint of supersymmetry. So it's baffling and maybe an exciting time that our first guess of supersymmetry doesn't seem to work. So what I wanted to describe is a little bit more sort of the quantum and classical mechanics of fermions and bosons. So I'm going to be a little bit slack with what exactly I mean here. I think that's fine. So for bosons, so these are the particles that like to stay together, they're all friends. Quantum mechanically, let's say we can describe two times, if you have two bosonic degrees of freedom, I'll call them A and B. So for those who know, you should think about position and momentum operators in quantum mechanics or annihilation and creation operators. Doesn't matter exactly too much for this point, but quantum mechanically, if I have a bosonic operator B, so AB minus BA equals something, equals this I H bar. So here H bar is Planck's constant. And if you see any equations with H bar in it, this should be telling you something to do with quantum theory, quantum mechanics, and so on. So bosons AB minus BA is this I H bar. I here is the square root of -1. Again, it doesn't really matter too much for our talk, how to think about this, but AB minus BA is equal some constant. Now for fermions, it just seems just the way it is, because they behave very differently, I can only put so many in a quantum state. It turns out that the correct generalization of this rule is this phi chi plus chi phi is IH bar. I guess again, I'm thinking about fermionic creation, annihilation operators. There are some other things like this. But notice that there's this sign difference in the middle. Yeah, so bosons, I've got this minus sign. Fermions, I've got this plus sign. Okay. So that's quantum mechanics.
Andrew, can I have a question, a quick question?
Yeah, of course.
Yeah, what are psi chi in the nature are? What the symbols behind?
Yeah, so this would be annihilation and creation operators for fermionic oscillators.
Okay.
Yeah, the operators. Yeah, or even more generally, they're going to be operator distributions and all sorts of things, but operators.
Operators. Okay, perfect. Thanks.
Operators. Yeah, so in classical mechanics, so go from quantum to classical, we can think about sending h bar to 0. So if I have some system, so h bar is a small number, it doesn't bother us exactly what it is, but this tells us the scale at which quantum mechanics is important. So if I have some system in which the scale of everything happening is much larger than this h bar, then h bar is small as far as we're concerned. We can essentially throw it away, set it to 0, and then we get sort of classical mechanics. So in this limit, h bar goes to 0. If I look then at the bosonic degrees of freedom, so now I'm thinking maybe more about sort of position and momentum in the classical sense, we see that this IH bar that goes to 0. So this tells us that AB equals BA. Okay, so this means that we call it commuting. So A times B is the same as B times A. So things you all know, standard numbers. If I take two numbers, I know 3 times 5 is the same as 5 times 3, so on. Okay, so bosons at this classical level, when you come to classical mechanics, we know it can then be described using numbers, or maybe functions take the values in numbers. But the classical boson, the boson degrees of freedom, these can be represented in terms of numbers, bog standard numbers that we all know and love. Now, if we do exactly the same thing for fermions, well, we've got this awkward plus sign in the middle for this quantum rule. So this tells us that phi chi equals minus chi phi. And we call this anti-commuting. So if I swap the order of these two things, I get this extra minus sign. This also implies that phi squared and chi squared equal to 0. So going from the classic, well, quantum to classic with fermions, we have this strange extra minus sign. So if I now think about, okay, in classical mechanics, if I want everything to be just numbers, what number can I have that phi chi equals minus chi phi and a squared to 0? Well, the only number there is 0. So in this sort of true full classical limit, there are no fermions. They all have to be 0. So instead of thinking that way, well, I'm going to have to not be thinking about numbers anymore. If I want to have a classical picture of these fermions, then I'm going to have to deal with some formal variables, chi's and phi's. And we won't worry too much about how exactly we think about those, but I can have some formal variables floating around, such that when I interchange the order, I pick up a minus sign. So the question is, so I can do geometry with numbers. I'll say about this in a moment. But can I come up with some geometry which takes into account these classical fermions? And the reason for this is there are lots of methods in classical mechanics and classical field theory that really are geometric in nature. Geometry can really help us understand the physics. And if we want to mimic some of these methods, then I'm going to have to think about geometry with things that anti-commute. Okay, so that's the story behind the next part, which is supermanifolds. Yeah, so before I talk about supermanifolds, I want to talk about what a manifold is. And again, I'm going to be very sloppy here. I hope not to tell you any untruths. But the idea, a manifold is a space. By a space, let's just think about a collection of points. There's no need to be much more careful than this at this point. But I have a space, some points, and if I pick a point, then I could sort of cut out a small piece of my space, and that's going to look like a small piece of what I call the p-plane. So a good example that you've all met, a practical example, is the notion of a globe and an atlas. So think about the globe on your desk. So that's a representation of the surface of the Earth. And so I know if I take any point on the surface of this globe, and that corresponds to a point in a chart, so on like a map, inside my atlas. So I have an atlas for nice loads of charts. And I know that if I take a point on my globe, I can go for my atlas, find a chart that corresponds to that point. And because of this, every point on my globe can be assigned 2 numbers. Yeah, the coordinates. So these are the coordinates associated to the chart in an atlas. So every point on my globe, I can describe it two numbers x and y. Yeah, so the longitude, latitude, or whatever they are in the particular example. So a manifold is essentially that. Yeah, I have some space, and every point with respect to some charts in an atlas, I can assign to it a list of numbers, the coordinates. So in general, I need p coordinates, so that's why I'm using this p plane. So every point, I have a chart associated with it, and every point that I can list, that p numbers that tell me this point. Right, so that's the basic idea of the coordinate geometry in manifolds. Again, always keep in mind this globe and this atlas is the sort of the standard example that you know and love. So a manifold is something like a globe, just need more numbers to describe each point. So what is a supermanifold? Well, to make this mathematically rigorous, it took a lot of work, it's a lot of machinery here. But when the dust settles, what is really happening is we just have a manifold, just as above, but now I have some extra coordinates floating about, some extra anti-commuting coordinates. So here I've labeled the whole collection as XA. So the first lot of x's with the small a, I'll call these even coordinates, x1 up to xp. Yeah, so here these are really just our numbers from the above example. And then I got to append to this q, let's say q of them, thetas, and I'll call these odd. So these thetas are going to represent our anti-commuting coordinates. So these are going to be variables that anti-commute, and I will treat them. So philosophically, I'm going to treat these just as if they were coordinates. Now, even though they're not numbers, there's something much more general. But for our purposes and for working with them, we don't need to think about that too much. Okay. So why graded? And why do I call them even and odd? Well, so by grading means I can attach an element of some set. Well, technically it's a group, but we don't need to worry about that too much. So everything to do with super, and the name comes from supersymmetry. But in mathematics, anything super tells you this set we call Z2 is floating around there in the background somewhere. So Z2 is just the set 0 and 1. So by grading these coordinates, I just mean that I assign 0 or 1 to the coordinates. So for all these x's, these even coordinates, so I use this tilde to tell me this is how I'm assigning this element 0 or 1. So x tilde is 0, which just means to all these x's, I'm assigning the number 0. I'm grading them with 0. Yep, same sort of thing then for these odd coordinates, these thetas, I assign them the number 1. So the grade is even, meaning that I'm attaching 0 to them. Yeah, is odd, meaning I'm attaching 1 to them. And the reason for that now is we can encode these commutation relations very neatly. So how I interchange the order of these coordinates. And it's done by, if I use XA, capital A, X at B, capital, so written down collectively, I swap the order. I pick up -1 to the grading of the first coordinate, grading of the second coordinate. So this is just zeros and ones, which means I just pick up plus or minus signs when I interchange the order. So if we go through this a little bit explicitly, when I was writing the coordinates out again in terms of even and odd coordinates, well, what happens? Well, if I take just the x small a, x small b, so these are just our even coordinates, interchange the order, yeah, nothing happens. Yeah, the order, just a plus sign. I can pass them through each other with no thought. Just as you do with numbers, I can always think about these x with small a's and b's. These are really coordinates onto manifolds. They're really just numbers. Now, if I interchange an x with a theta, here's something even, something odd. Again, it turns out by this rule, I just pick up a plus sign. I can pull them through each other with no problem. The more interesting one is when I have the odd coordinates. So an odd coordinate. If I change the order of those two, given by this rule, I pick up this minus sign. Yeah, and of course, then we have that any of these thetas squared equals 0. So all I've done is I've append these sort of fermionic, as we say, variables to our manifold. So I think about these then as being coordinates. They're not really coordinates in the classical sense because they're not numbers, but almost all of differential geometry, so all of the geometry of manifolds, particularly if I think about these coordinates in this way, most things generalize without too much work. Just got to be a bit careful about plus or minus signs. So the word of warning here with these supermanifolds is when we generalize from manifolds to supermanifolds, what causes most of the technical problems is not so much this minus sign wanting to change two odd variables. It's really I have variables that square to 0. This is what we call nilpotent coordinates, or things that square to 0. This is where most of the technical problems lie in going from manifolds to supermanifolds. Okay, but we won't say anything about that, just a word of warning. Okay, so that's supermanifolds kind of done and dusted. But there are plenty of hints, well, from the theory of supermanifolds, also from algebra, and maybe some hints from physics as well, that super is just not really enough. Again, we should be thinking about grading things in a different way, and this leads on to the idea of these higher gradings that I've been working with. So what's the idea of what I call a Z2N manifold? So this is Kovalov, Roboski, and Ponsin about 2016. Worked out a lot of the details of what these Z2N manifolds are to concretely very carefully. So I won't do that. I will just take this coordinate approach to sort of sketch what's happening. So in particular, I won't even think about Z2N. I'll think about Z22. So Z22 is simply 2 copies of Z2. So I have 0, 1, and 0, 1 is both these Z2. And I take this product, bring them together. So what I get is a list of 0, 0, 1, 1, 0, 1, 1, 0. So we're going to play almost the same game as we did with supermanifolds, but now we're going to use this higher grading, these 2 copies, to grade the coordinates, and use this to decide what happens when I interchange the order of the coordinates. So for a Z22 manifold, so I'll suppress all the indices, so there may be more than one of these coordinates of each kind. But I'll have x, z, theta, eta. So the first 2 are going to be even, second 2 are odd. So I'm going to assign elements from the Z22 to them, and I'll do it in this way. So the first coordinate x, this is going to be 0, 0. So I'm going to attach this list 0, 0 to this x. For z, I'm going to have 1, 1. So I'll call these even coordinates because if I sum 0, 0, that's 0, that's even. 1 plus 1 is 2, that's even. Yeah, I'll call these even coordinates. And similar things if I had Z2, 3, and so on. Yeah, just have longer lists of zeros and ones. But anything in which the sum of the 2 components is even, I'll call that even. And one thing to note immediately here is that this x, so as before with the manifolds, yeah, this can be a real number. Yeah, I mean, we can still think of it that way. But the z, it carries this grading 1, 1. So the z itself is again similar to the theta from before. It is a formal object. It's a formal coordinate. I shouldn't think about this as really taking values as numbers. It's something more general than that. So the odd coordinates, same sort of thing. So now I have theta and eta. I'm going to assign 0, 1, 1, 0. So again, these 2 are very similar to the theta in the previous description of supermanifolds. So that's how I'm going to grade these coordinates. And I realize that x could be a sort of a genuine coordinate. All the rest of them, these are now formal things. They don't take numerical values. So the commutation rules, so how I interchange the order of these things, this is defined by this Z2 grading. So how I've attached these zeros and ones to each coordinate. And then I need to have a sign factor. Yes, I need to decide what happens. And we can use this, this -1 to this bracket, as I've written it. So this bracket is the canonical inner product on Z22. So what you should be thinking of with this inner product are things like the scalar product from high school. Okay, so just to show you how it works. So if I want to take this inner product of 1, 1, 1, 0, for example, then all I've got to do, it just tells me I take this first entry, this 1, multiply it with the first entry and the second one. Yeah, so that's 1 plus 1. Then I do the 1 times the 0, add it to the other one, so it's 1 plus the 1 times 0. So I get 1 plus the 0, that's just 1. So I write this list out, I take the first one, multiply it with the first one, plus second one with the second one, and in general, it'll be third with the third, fourth with the fourth, and so on. There's no more than the standard dot product on our end. So now I put this into my formula for this sign factor, it's -1 to this product, and in this case, I pick up, well, it's -1 to the 1, which is just -1. Again, I use this -1 to decide what happens if I interchange the order of the coordinates. Okay, so writing them out then, so I won't write down XX. Yeah, that just commutes the order of X, nothing happens, I change the order. So now if I look at X times Z, so that's even and even. So I now change the order, so ZX. Now following this rule from above, I just get the plus sign. So if I have an X and a Z, I can push them through each other, no problem. Exactly the same then with the X theta and the X and the eta. So this is really just the same as the supermanifold case. Yeah, I just have my X, I can push it through the thetas and etas, no problems with the sign. It's now more interesting when I come to this Z, because the Z carries this degree 1, 1, and we have this funny sign rule. So Z times theta. So Z is 1, 1, but theta is 0, 1. We notice with this product, so it's, we're going to pick up -1 to the 1. We now have a minus sign. So Z theta is minus theta Z. Exactly the same sort of thing for Z and eta. I interchange the order, I pick up this minus sign. And if I interchange thetas and etas, I pick up a plus sign, not a minus sign. But I still have that theta squared is eta squared is 0. So that looks very much like the super case. And now I have this Z, which is a formal coordinate. So it's not a number, it's something abstract. If I square that, it's not 0. So this is very different to the super case. So in particular, I have an even coordinate, the Z, that can anti-commute with odd coordinates. Yeah, I pick up this minus sign for this theta and eta. This is very, very, very different to the standard super case. And I also have odd coordinates, so this theta and eta. If I interchange their order, I get a plus sign, not a minus sign. So again, this is just very, very different to supermanifolds. Okay, so that's the idea with these Z2n manifolds. So a manifold is some space, whatever that means exactly, but I can take a small piece of that. That looks like a small piece of this P plane. Every point I can assign P numbers to it. Supermanifold, bit similar. Very heuristically, I can take a small piece of my supermanifold and I can then use coordinates. So I now have my X and my theta. The important thing is theta, so I interchange their order, pick up a minus sign, and this go to 0. Z2n manifolds, very, very similar again, but now, particularly the Z22 case, I have more coordinates with slightly more complicated rules when I change the order. But heuristically, it's just coordinates that swap the order, pick up plus and minus signs. So one of the technical problems, I said, when going from manifolds to supermanifolds, was the fact that we have coordinates that square to 0. This is what causes the headache, going from the classical picture to the super picture. Going from super to the Z2n, we now have to contend with formal coordinates, in this case, the Z. So for higher gradings, so for Z23, Z24, and so on, there'll be a similar situation, where there'll be even coordinates that are formal, that don't square to 0. And this is what causes the problem going from supermanifolds to Z2n manifolds. It's kind of coming back full circle to some extent. So it's this formal coordinates that don't square to 0 really, really causes the technical headaches when dealing with these things. Okay, so now I want to spend the last sort of 5 minutes or so roughly sketching some of my contributions. So I won't be able to say too much because a lot of it's not unexpectedly quite technical. So since about 2016, I've been working on Z2N manifolds and some related questions in physics. So particularly with Ponson and Grabowski, so Norbert Ponson in Luxembourg, Janusz Grabowski in Poland, look at Z2N geometry or Z2N manifolds. The first thing we looked at was a lot of the technical properties. So, okay, there's early papers that define lots of things, but there are lots of technical questions about these Z2N manifolds. A lot of nice properties that manifolds and supermanifolds share that allow you to further develop the theory carefully and properly needed to be checked. There are lots of things that were not surprising, almost obvious, I would say, at least the statements, but proving them was extremely difficult. So we had lots of almost obvious statements that in the super case, these were like 2 or 3 lines proofs, some of them. These are now 2 or 3 pages because of this. Yeah, we have formal coordinates that didn't just disappear from our expressions because, you know, z squared, z cubed, so not 0. There's just a lot of problems associated, just technical problems to check associated with this. Plus, with the more and more degrees, there's just more to check. But the real headache is when things like the z squared doesn't go to 0. Bottom line is, for this first part, the technical properties, I won't say what they are. We can discuss it afterwards if anybody's interested. Everything we checked, yes, it works. So Z2N manifolds do seem to be a reasonable geometry. We have a lot of the technical properties to do with, well, the functions on them, the properties of the sheaves of functions. It all seems to be nice. All seems to work is the main point. The other thing we checked, particularly now with Janusz Grabowski, with Riemannian and symplectic structures. So again, I won't say too much, but a Riemannian structure is something vital in, for example, general relativity. And symplectic structures are the geometry behind classical mechanics. So these are 2 well-studied geometries in the classical setting. Question was, are there any problems in the Z2N setting? Well, before that, of course, it's well known in the super case. Yeah, these things are well defined. The main theorems in the classical setting generalize to the super case. And again, we prove the same sort of thing. So that the Riemannian geometry and symplectic geometry do generalize to the Z2N case. It's a bit more freedom with how things work because we have a larger grading. So there's a lot more to check. But again, same with some of these technical properties. Some of the, well, all the statements I would say, again, are not particularly surprising. They follow from the classical or the super case rather directly. But proving them again, some of them were, well, some were straightforward. And other things we had to really work a lot harder to really nail down the proofs. So again, the statement is lots was obvious, but absolute nightmare to prove. So with the geometry, the story seems to be it's working well. It seems to be a reasonable geometry to try to work with. So a spin-off from that I did at the same sort of time really was looking at Z2N graded supersymmetry. So part of this is done with Stephen Dupley. I'll mention his contributions a bit more in a second. But for those who know, so I proposed, was it 2019, I think it was, a higher graded version of superalgebra and superspace. So basically, this is just the algebraic and geometric setting of standard supersymmetry, which is Z2 graded. I worked out, well, a sensible version in the Z2N setting. So now we don't just have Z2, we have this Z2N sort of lying behind it. So it was an attempt to generalize these superspace methods for those who know about that. The other thing I did, and this was particularly with Stephen Dupley, is we developed the first quantum mechanical model with this higher graded supersymmetry, okay, in the n=2 case. This was a generalization of Witten's model. It seems to be a very simple model, maybe too simple, but it showed that we can have this Z2-2 symmetry realized in sort of simple quantum mechanical models. So that spurred on a few other people to generalize some things, work out some other stuff. particularly Francesco Topan in Brazil. He really picked up on this and developed some classical mechanical models as well. So I've been less involved in the classical mechanical models, but I was the first one to develop a field theory that has this kind of symmetry, in particular the first sigma models. So these are models just in 2 dimensions that have this new kind of supersymmetry, again in the n=2 case. So there's a nice sigma models that I managed to generalize with a bit of work to this, having this new kind of supersymmetry that I proposed. So without too many details again, this isn't so easy. There's a few sort of problems along the way. And the first one was quite interesting with these sigma models particularly. And same thing occurs actually in the classical mechanical models. If we want some models in which the different particles interact with each other, so they talk to each other, then we seem to need graded parameters. So in the Z22 case, in particular, it was just needed to have some parameter that was graded itself 1, 1. So from a sort of classical picture, it's not clear exactly what I mean by a parameter that's graded 1, 1. It seems very, very strange, but it seems to be needed. So because my own thinking is this is really just an artifact I'm dealing with a classical model or a quantum one. And maybe somehow when we quantize it, it'll become a bit clearer what on earth these graded parameters really mean. But that is very speculative at the moment. I really don't know. So the other thing that was difficult, particularly generalizing these superspace methods, is I needed a theory of integration on Z2n manifolds, or even just on Z2n manifolds that just in the 1 coordinate chart. This has really not been developed. So for those who know a little bit about supermanifolds, so integration on manifolds, this is an old story, well done. Passing to supermanifolds, it's a lot more complicated, but that's known, that's done. Taking this now to the Z2n case has been a complete nightmare. Yeah, so the integration theory here is just not developed at all. So I contributed to that in a small way. We're working with these sigma models, but yeah, without integration theory in place, it's not immediately clear how we can continue to develop the standard methods used in supersymmetry. And I already mentioned the physical interpretation of all this. So I have this higher supersymmetry. I have some models in low dimensions, particularly. Are they interesting in physics? What's the real connection? Are we just doing mathematics? Don't really know at this point. So Z2 gradings seem fundamental in physics because we have these fermions and bosons. This is definitely Z2 graded. Yeah, and we know these things exist. There's no question about this. With these higher gradings, it's not so clear what we mean here, though there are some links with what we call parastatistics, so particles that are actually not bosons or fermions. We have good reason to think in 4 dimensions, so 3 space, 1 time, that we only do have bosons and fermions, but the theorems here are technical and there could be loopholes. And so I'd say it's not completely sorted whether we really do have to have just bosons and fermions. But certainly that nothing else has been observed yet. There is an suggestion that some of these strange particles could be dark matter, but I'm not sure about that. The other place where these strange things could appear is in condensed matter physics. Because, so these theorems that tell us we only have bosons and fermions apply in 3 + 1 dimensions. If I go to 2 + 1 dimensions, then these theorems just don't hold. So it's possible we can have parastatistics in condensed matter physics, and this could be somewhere where my Z2 or Z2n supersymmetry could possibly be realized. If it's going to have some physical interpretation, some physical realization, I think it's going to be there rather than in sort of fundamental high energy physics. But that's just my feeling at the moment. So just to tell you what the Z2n supersymmetry is, or Z22. So if you remember at the beginning, I had this diagram with the bosonic state, or bosonic particle and a fermionic particle, and supersymmetry really is an arrow between the two. I could take one, map it to the other one, and back again. So now here in the Z22 case, I have a lot more particles, a lot more types of particles. So I have a standard boson, which we call here B. So that's associated with 0, 0. I have what I call an exotic boson. This associated with this 1, 1 sector. We call that E. And then we have two types of fermions, so type 1, type 2, 0, 1, 1, 0. So before we had just fermions and bosons, now we've got a boson, some exotic boson, two types of fermions. And this Z2 supersymmetry, what it does is it takes, let's start with this boson. I can map it to the fermion of type 1, or back again, yeah, or I can then map it, this fermion type 1 to this exotic boson. Or I can go the other way from the boson to the fermion of type 2, then to the exotic boson. So instead of having just 2 arrows horizontal, I've now got these 2 arrows vertical and twice as many types of particles just in my theory. So I think I'll stop there. This is, again, a very quick, rough sketch what I've been doing for the last few years. So if that's okay.